This last problem deals with a specific example of the construction with finite fields where we take z mod 2z and we extend it by creating a root of a new quadratic. So let's start by recording the information. We start with z mod 2z as a field, which Pinter abbreviates to z2. We adjoin x, and then we set x squared plus x plus 1 equal to 0, which he denotes with the angle braces like so. And what we saw in the main video for the big theorem for this chapter is that we can essentially do the Euclidean algorithm, or sorry, the long division algorithm on any polynomial that you like to reduce it down to something like degree less than 2, since I'm dividing out by this degree 2. Or said a different way, setting x squared plus x plus 1 equal to 0 is the same thing as setting x squared equal to negative x minus 1. And actually in z mod 2z, 1 plus 1 is 0. So 1 is equal to minus 1. So this is the same thing as x plus 1. I know that's like super weird, and z mod 2 is really weird. It's just a general quirk about z2. And so what this exercise asks us to do is, after we understand that, let's come up with the 4 elements of this new field extension, and let's work out their multiplication and addition. So we have the original field elements, namely 0 and 1, but I also have now x and x plus 1. And actually that's it, because once I go up any higher than that, anything involving x squared, I can reduce it down. So, if you had x squared plus 1, I would write x squared equals x plus 1, and then I would get x plus 2, which is the same thing as 0, since 2 is equal to 0 in this object. And so this thing would simplify down to that. So here are my 4 elements of this field. The first thing I want to point out about this is that we can see that this will happen in general. So if you have a z mod pz and you factor out by some polynomial, which we could call big P, whatever the degree of big P is, after making it monic, since you can always multiply through by multiplicative inverse of the leading coefficient, you'll be setting degree of big P equal to some, x to the degree of this big P equal to lower order stuff. And how many lower order thingies are there? Well, for every lower order that's possible, there'll be P of them, right? Because you have P possible coefficients coming from z mod pz. I'm realizing that I'm using the letter P in 2 different ways, and that's a little bit confusing to listen to, so I'm sorry. The point is, the fundamental counting principle says I'll have P choices for constants times P choices for linear times P choices for quadratic, and so on. You will get some number of P's. And so in this way, I can cook up a finite field which has P to the n elements for any P, any n, as long as I can find an irreducible of degree n. And it turns out you can actually for every n. There are irreducibles. This leaves us with a question, which we're not going to answer for this video, but just like some food for thought as we, you keep learning this material and think it over. Are these isomorphic fields? Surely they can't all be isomorphic, right? Right? Which ones are possibly isomorphic to which other ones? That's the question. I'm not going to answer that right now, but it's just something for you to think about, because what I've shown here is we started with a field with 2 things in it, and by extending by degree 2, I ended up with something of order 2 squared, right? Because there were 2 coefficients of lower order, namely 4. So it's very reasonable to ask, how does z mod 2z adjoin x mod x squared plus x plus 1 relate to the field that you get if you ignored this guy, right? Just modding out by x squared plus 1. Are those isomorphic or not? Maybe that's a nice little question for you guys to think about. Anyway, that tangent aside, let's work out the addition and multiplication. So we have It's all commutative, so it's symmetric. We have 0, 1, x, x plus 1. Of course, when I add 0, we know how that goes. When I add 1, I get 0. When I add anything to itself, right, I get 0, because when you add something to itself, you get 2 of it, and 2 is 0. So these guys are all 0. This guy is x plus 1. This guy is x plus 1. This one is, this x cancels with this x, leaving just 1. And here, this 1 cancels with this one, leaving just x. So here's our addition table. Now we have to do a multiplication table. These ones tend to be a little bit more work. Not a huge amount more work, mind you, but a little more work. In fact, let's save ourselves some headache. Let's just remove the 0, right? Because multiplying by 0 is very boring, right? We know that fields, after you remove 0, are an abelian group. Friends, it's an abelian group of order 3. What abelian group is it? Oh, we're so stoked to know group theory right now, right? We can fill out the table. Of course, I could just multiply these out. But also, because this is a group of order 3, right, we could call this, I don't want to call it Z. I don't want to call it anything misleading. Z mod 2Z join X. Let's just write, right? Modulo this guy. The order of this is 3. Oh, sorry, that's not true. It's 4. Hold on. Minus 0 equals 3. Therefore, it is abstractly isomorphic as a multiplicative group to Z mod 3Z. Stoked. Let's see that that's true. X times X is X squared, which we saw is equal to X plus 1. X times X plus 1 is equal to X squared plus X, which is equal to X plus 1 plus X, or 2X plus 1, or just 1. Amazing. And now it's commutative, so it's symmetric. We have to do X plus 1 squared. Could do that a couple clever ways. Like I could do what I just did and modify this calculation, but let's use our binomial stuff. Right? So now we got 2 simplifications. This guy goes away. He's 0. X squared is equal to X plus 1. These guys go away. We just get X. But if you didn't know that, but you knew it was an abstract abelian group under multiplication, you would just use our Sudoku rule, right? It's the only thing missing. And so we can understand how the arithmetic of fields works using our group theory knowledge. And in general, we don't have to go through quite as much work. There's one last trick which I feel like I should probably make mention of. How long have I been talking for now? Only 9 minutes. So there's one last trick that I should probably make mention of. For those of you who know linear algebra, then you know that multiplication, because it's distributive, multiplication is a linear function. And so therefore, there will be a matrix representation given by the linear map, where you take a given A and you multiply it by whatever you're interested in, for example, X. And so you can use that matrix to speed up calculations in bigger cases. If you don't know what I'm talking about, don't worry about it too much. It's fine. And I'll probably show an example down the line where we do some stuff like this. In any case, I think this is a good place to stop here. And so take a look over the problems listed in the homework. And if anything comes up, you guys know where to find me.